So now that we got formulas in that easy special form, how do we actually prove things with these formulas? How do we avoid that big question of which rule of natural deduction we select and where exactly we apply it? What people do when they write automated provers is essentially applying only one rule, the resolution rule. Just a reminder, here is what it looks like. And at least this is what it looks like in the special form that people use in automated provers. They apply the resolution when they have two clauses, one of which has some variable as a positive literal and another one has the same variable as a negative literal. And what the resolution rule says is that once you do it, you get another clause, another OR of things, which contains everything else in C other than X and everything else in D other than not X. Let's see some examples. So suppose you have clause Y or not Z or W, and another clause that has U or not W. So in this case, you have W, which is a positive literal in the first one, and the same variable W, which is a negative literal in the same one. So we could just take everything else in those two clauses and merge it together to get a clause Y or not Z or U. So what happens if you have a duplicate literal? For example, here you still have W and not W, but in addition you have not Z in both of them. Well, you know that anything or the same thing is whatever you started with. P or P is equivalent to P. Not Z or not Z is equivalent to just having not Z once. So all you do is just you remove duplicates in the resulting clauses. Y or not Z or not Z is the same thing as Y or not Z only once. So finally, what happens if your clauses have only that literal and the other clause has only the negation of that literal? What if your first clause is W and your other clause is not W? In this case, you get an empty clause. You get an OR of nothing, which is false. Or another way of seeing it is, wait a moment, when you go to something is true and something is false at the same time, that's a contradiction. That's exactly what we are using here. So how can we use resolution to prove things, to solve problems? Where resolution really shines is finding inconsistencies. So if you have a list of logic statement, A1, A2, and so on to AN, remember that they're inconsistent if the end of them is contradiction, is unsatisfiable. There is no way to make it true. And remember that we were saying that you could derive false as a conclusion from a list of premises that are inconsistent. And that was if and only if. So in order to check whether your list of statements is inconsistent, you could check whether you could derive false from it. And what does it mean to derive false? Well, it's enough to have some literal W and some literal not W, and you could apply resolution rule to them and get the false. So if you have a more complicated statement, P or Q, P or not Q, not P, you may need to apply the resolution rule several times, and eventually you will derive false. So here's how resolution refutations work. By the way, we are calling them refutations rather than proofs because we are refuting, we are proving that something is false rather than proving something is true. So what resolution refutation is? It's a proof that the list A1, AN is inconsistent by proving that A1 and AN and so on is a contradiction, and that we prove by applying resolution rule repeatedly to get false. Here we often think about a list of clauses in a CNF and an end of clauses of a CNF sort of interchangeably. From the resolution point of view, it's kind of the same thing. So if you derive false, then A1 and so on AN was unsatisfiable, a contradiction. So every scenario makes it false. But maybe it wasn't false. Maybe there was some scenario that made it true. What would happen if you keep applying the resolution rule? Well, in this case, you just run out of possible places to apply your rule. And if you run out of possible ways to apply the resolution rule and you still didn't get the false, then you can actually reconstruct the scenario which makes your formula true out of whatever you managed to derive. So here's how we are doing a resolution refutation. So we start with a list of clauses or an end of those clauses. And at every step of the refutation, we pick two clauses such that for some variable, one of those clauses has this variable, and another one has its negation. And then you derive a new clause, C or D, by using the resolution rule. And when you do it, you add this new clause to the list of the clauses that you already have. So you originally had n clauses, or maybe more if some of those A1, AN were CNFs that contain more than one thing. And every time you do the rule, you throw in one more thing into your list of clauses that you know. Those are the list of your assumptions, a list of facts that you know or you derived. You never throw things out. And then you repeat it until you derive false. So let's do an example. So suppose you have clauses y or not z, not y, and y or z. Let's try to derive false from those clauses. First of all, if you were to do a truth table here, you would notice that there is no way to make all those three things true at the same time, because y has to be false in order to make the middle one true. But then to make the first one true, z has to be false, and to make the last one true, z has to be true, and cannot be both at the same time. But let's just do a resolution refutation. So let's pick two clauses. For example, we could pick the first one and the second one, or we could pick the first one and the last one, or we could pick the second one and the last one. Let's pick the first one and the second one, because the first one has a y and the second one has not y. And we could resolve them to get a clause containing just y. Sorry, just z. Similarly, we could resolve not y with the last clause to get z. Finally, when we have not z and z, we could get false. And here it is, your resolution refutation. You only needed 3 steps rather than writing the truth table. Well, the truth table here is not that big, but still, you use fewer steps to get your answer than you would with a truth table. So here is a less pictorial way to write down what you were doing. So you started with 3 clauses, y or not z, not y, and y or z. The first thing you did is you derived not z, that's your clause number 4 in your growing list, from clause 1 and clause 2. Second thing, you derive clause containing just z from 2 and 3. And finally, you derive false from 4 and 5. So one thing to note here is that we really needed to use the second clause in 2 different places. We needed it to derive not z, and we needed it to derive z. In general, you could use those clauses multiple times, as many times as you need to. And actually, this is what allows those proofs to be so big. That's because sometimes you use clauses so many times in so many different combinations, then you end up just with a gigantic proof. Nothing wrong with that. It's better than not having a proof at all. I really wish we knew how to do it faster. So let me show you a slightly different view of resolution refutation, which is a little bit more algorithmic. So here is a refutation that we just did. Now let's think about it in an upside down way, as a decision tree. So a decision tree is a computer science structure where at every point in time you ask a question, and depending whether the question came up yes or no, you may be asking other questions, and you keep doing it until you figure out what the answer should be. So for example, we start by looking at the variable z, and we ask, is z true or false? Okay, suppose that it's true. Then we know that y has to be true. Well, actually, in fact, if it's false, we also know that y has to be true from the last clause. And if it's true, then we know that y has to be true from the last clause. And if it's false, we know that y has to be true from the first. Okay, so suppose y is true, addition to that. Then it's a problem because with this scenario where z is true and y is true, not y cannot be satisfied. There is no way to make the second clause true. Okay, maybe setting y to false would help. Yeah, it would help to make not y happy, but then y or not z doesn't work. Similarly, if z is false, can we possibly find a scenario where the whole thing is true? Would it be true when y is true? No. Would it be true when y is false? No. Well, we kind of essentially reproduce the truth table here, but sometimes you don't need to make so many steps and look at all the possible scenarios to find out the answer. For example, if we would have started asking about y rather than asking about z, we would know right away that y cannot be true, because that would make the second clause false. And we would only need to look at two scenarios with z. So let's do a big example of a resolution refutation. So here there are lots of places where we could start. For example, the first one and the first clause and the second clause, they share several literals. The first one has x, the second one has not x. Actually, in fact, the first one has z and the second one has not z. Also, if you look at the third clause, it also has a not z, and where the first one has z, so here's another pair that we could start with. Yet another could be we could start with x or y, which is our clause number 5, and get something out of that one, and maybe the very last clause, because clause number 5 has x and the very last one has not x. So here you're free to pick any two clauses that have opposite literals. So let's pick something simple. Let's pick things in the middle, y or not z, and not y or not z. So if we apply the resolution rule, then the remaining part in C as well as the remaining part in D is not z, and as we remove duplicates, we end up with something that just has not z in it. Now we could use the freshly derived not z, or we could use some other clauses. So for example, you might want to say, let's now do resolution on the first two clauses, x or not y or z, and not x or not z. But here's the caveat. What would you get if you try to resolve those two clauses together? From the first one, you get not y or z. From the second one, you would get not z. So you get not y or z or not z. But wait a moment, z or not z is always true. So you would get something that's always true, and it's kind of useless for trying to derive false. So let's do something else instead. Maybe let's do the clause that we freshly derived and combine it with the very first clause. What do we get? So the first clause has z, the one that we just derived, which would be number 7 in our list, is not z. Nothing remains in the clause we just derived, but x, not y, remain in the first clause, so we end up with x or not y. Okay, we have x or not y, and somewhere else we had x or y, which is great because it would let us derive something new. It would let us derive x. So if only we could get a z from somewhere, or if we could get a not x from somewhere, we'd be able to derive false. Let's try to get not x from somewhere. Where can we get it? Well, second clause has not x, and the last clause have not x. We cannot really get not x out of the second clause right now because we only have not z, and it's the same not z as in the clause number 2, so we cannot really resolve them. But we can resolve not z with the very last thing, so let's do it, and that gives us not x. Great. Finally, we've derived a variable, and we've derived its negation. Something and not the same thing cannot be true. We get a false. And there it is, the proof. So notice a few things about this proof. We never ended up using clause not x or not z, and it's perfectly fine. Your list of premises is still contradictory, even if you throw some extra things there that really don't affect anything. If I say today is Monday and today is not Monday and I have a class, you know, it doesn't matter if I have a class or not. Today is Monday and today is not Monday is never going to be true. Another point is that we use the clause not z that we derived 2 times. Just like in the example before, we used not y 2 times. In general, it can be any clause that looks whichever way it may look, that you may end up using maybe 2 times, maybe 5 times, really depends on your proof. So in a resolution refutation, you're really looking at your clauses as a list of some kind of facts. And some facts may be useful in more than one place. Some facts may be completely useless to derive a contradiction. But as long as you could show that somewhere in your list of facts there is an internal contradiction with a resolution rule, multiple applications of it, then you have proven with a resolution refutation that your list is inconsistent. So let's have a puzzle. Suppose that nobody in our class carries more than 10 pens on them. And let's say there are 108 students in our class. How would you prove that there are at least 2 students in our class who carry the same number of pens? In fact, you could prove even more than that. You could prove that there are 10 students in our class who will all have the same number of pens on them.